Good morning. Today we're going to start Chapter 7. Chapter 7 is entitled Estimates and Sample Sizes. And the first section of Chapter 7 is 7.2, Estimating a Population Proportion. Alright, let's think for a minute. Let's say we've got a huge population. And we're interested in a population proportion with some characteristic of interest. Any characteristic you like, I suppose. Population proportion we symbolize with a lowercase letter p. All right? Now, p, because we're talking about a population, populations are too big to study, and really the value of p, little p, is unknown and really unknowable. Too many elements to count, perhaps millions, even billions, unknown and unknowable. So the only way we can consider p is really to make estimates, right? So p, little p, population proportion with some characteristic of interest unknown, what we're going to do is estimate p. And the first way we're going to estimate p is to create a point estimate. You can create a point estimate of little p. Again, population proportion with some characteristic of interest. Alright, what we'll do at first to estimate little p, we can take a sample, right? Take a sample from our population. This is the big population. Here's a little sample. And from this sample, we can compute a sample proportion with some, again, desired characteristic of interest. Our sample proportion we will denote with the symbol p hat. P with a little caret symbol on top of it. Alright, now p hat is defined as, well, a raw count with some characteristic of interest divided by the sample size. So let me make a note of that. Let me make a little note here. X would be our, I'll call it a raw count of items in the sample with some desired characteristic, and n, smaller case n, of course, would be our sample size. Okay? So p hat equals x over n, and we can call p hat a point estimate of little p. Remember, little p is our population proportion, and p hat will be our sample proportion, again with some desired characteristic of interest. Let's take a look at an example in the book. I believe this is not a book example, one I cooked up here. Let's say I want to estimate the population proportion of left-handers worldwide. Of course, worldwide we can't come up with that exact value. There's billions of people to count. Alright, well, what I can do, the next best thing I do is take a sample, right? So let's say in a sample of 677 people, we find 88 are left-handed. Alright, so that means our sample proportion of left-handers is going to be the number of left-handers, the raw count of left-handers, divided by the sample size. And here that would be, of course, 88 over 677, and that's 0.13. So In our sample, about 13% of our sample was left-handed, and we will use that as a point estimate of the population proportion, right? So we claim that p hat equals 0.13 is a point estimate of little p, where little p is the population proportion of left-handers worldwide. All right? We call it a point estimate because this value occupies 1 point on the number line. All right? So it's a single number value estimate for p. All right? Well, the idea here is we might have a problem with estimating population proportions in this way. Well, is p hat a good estimate of little p? Well, because p hat depends on sample information, and by definition it's a sample proportion, right? Well, the sample may be a good indicator of the characteristic worldwide. It may not be a good indicator or estimator of the characteristic worldwide. Perhaps this is a good estimate. P hat is a good estimate of p. Perhaps there's a better way, right? We can create what we call an interval estimate of small p. Right? Well, sometimes we call these confidence intervals. Right? Confidence interval estimates of p. And what we're going to do is create not just a single value, p hat, to estimate p. What we're going to do is create a range of values. Kind of a bucket, you might say, which hopefully would catch little p, if you will. Alright, to create this confidence interval estimate of p, I'll compute what we call a margin of error, alright, and successively add and subtract that margin of error from p hat to create a range, again, which hopefully will contain little p. Right? Well, in the end, we'll claim that p, little p, will fall within this range with a certain probability or a certain level of confidence. All right. Well, and overall, this is what a confidence interval is going to look like. This range is going to be my confidence interval estimate for little p. Okay? All right. Let's get some terminology down here. Level of confidence. How strong do we want to be assured that little p falls in the above ranges? All right? Well, that is determined by what we call a level of confidence. Now, level of confidence is defined as 1 minus alpha. We'll talk more about alpha later. Typical values of level of confidence are 0.9, 0.90, 0.95, and 0.99, kind of low, medium, high for our levels of confidence. And of course, you want to be as confident as possible, we suppose, in any experimental setting. So these levels of confidence, these probabilities, range kind of high, on the high end of things, right? Near 1. Our margin of error. Right, that's going to be our cap E. Now there is a formula for cap E. It's a fairly nasty looking formula. Right. Well, the most important thing about this margin of error is that it depends on a z-score, right? Which depends on an alpha level. Right. Now, the calculator will compute this value of E in upstream calculations, as we'll see. Upstream. Right. But I do want to give us the formula here, and note that the value of E does in fact depend on a z-score. All right, p hat, of course, is your sample proportion. Q hat, kind of goes without saying, is the probability complement of p hat. In other words, 1 minus p hat, and little n is the sample size. All right, we won't be using this formula directly, but certainly the calculator will be computing our margin of error upstream. Okay. Our confidence interval for P can be expressed in a few different ways. It can be expressed graphically, as we saw before. You can get a range of values depending on p hat and our margin of error. It can be expressed in interval notation, where we've got parentheses and the hopefully familiar interval notation with a min value and a max value indicating boundaries for our range, and also an inequality notation. And I believe the author indicates the confidence intervals in their solutions manual pretty much in this double-sided inequality notation. Our calculator will output our our confidence intervals in this interval notation. So be aware of that. I suppose we should be comfortable with both notations, interval notation and inequality notation. Okay? Alright, now we're going to find out how to actually compute these confidence intervals. Alright, let me get a fresh screen here. Alright, to compute confidence intervals. On the TI 83 or higher, we're going to use a command called 1prop z int. Alright, 1prop because we're going to be estimating one population proportion. Z, as you recall, the formula for margin of error depends on a z-score, so Z for z-score, and int meaning confidence interval. Alright, to get to this command on our calculator, it's pretty easy. We click on Stat, hit your Stat button. Alright, in the submenu that appears at the top of the screen, you'll want to scroll over and select Tests and Enter. Then you'll need to scroll down, and you got to scroll down pretty far on the calculator, whatever calculator you've got, the 83 or the 84, and choose 1prop z int on that list, and then enter. And you will see the calculator then prompts you for the following values. You need an x value, well, that's a raw score in your sample with a characteristic of interest. N is, of course, your sample size. Confidence level will be a number, well, typically near 1, either 0.9 or 0.95 or 0.99. And once you've entered in those values, you'll then type in, or select, I should say, calculator, calculate, and then hit enter to display the calculator's results for the confidence interval. Let's jump in and do an example of how to use this command. All right, I'm going to look at example 3 on page 331. Hopefully you'll get your book there. You can turn there yourself. Let me turn there. .331, give me a second. Alright. Example 3, page 331, constructing a confidence interval poll results. In the chapter problem, we noted that a Pew Research Center poll of 1,007 randomly selected U.S. adults showed that 85% of the respondents know what Twitter is. The sample results are n equals 1,007 and p hat then equals 0.85. I want to look at part B. Find the 95% confidence interval estimate of the population proportion P. Alright, let me write down some stuff here. Well, we want to find out a population proportion, or estimate a population proportion of people in the world that recognize Twitter. Alright, well, we'll never know that number for sure, but we can estimate it, and that's what we're going after here. Alright, so we'll use a sample of 1,007 people. We know that the sample proportion of people who recognize Twitter in this sample is 0.85 or 85%. Alright. Alright, so we need a 95% confidence interval estimate for little p. Okay? Alright. Well, if we go to the command, the onePropZint command, well, the first thing we'll need is a raw count of people in the sample that recognize Twitter, and we don't have a raw count, right? So we'll need an X value. Well, if you've got a sample of 1,007 people and 85% of them recognize Twitter, I don't think it's too much to expect that we can find the raw count by multiplying 1,007 by 0.85, right? Alright, so X, our raw count for people who recognize Twitter in this sample, is approximately 856, let's say. Let's round off to the nearest integer. Often when you're given percentages like this, your raw count will come out as not a whole number, so we'll just round off to the nearest whole number. Alright, so now we do have a raw count. Alright, in some of the problems in the book, X is given to you explicitly. In this one, X is not given to us explicitly, and we've got to do a little bit of a calculation to get there. So be aware of that. Alright, we're ready to find our onePropZint command now. Click on Stat, punch Stat button, scroll and highlight and enter on the Tests option for the submenu. Again, scroll down till you find onePropZint and select and enter, and you should have an input screen that looks like this. Alright, you're asked to input a raw count for the number in the sample that recognized Twitter, and of course that's 856. Right. For our sample size, of course, that's explicitly given to us is a 1,007. And our confidence level, well, we are asked to create a 95% confidence interval, so I'll put in 0.95. And when I've input all those values, I'll select, calculate, and enter, and I should get the following output. Now again, the calculator outputs these confidence intervals in what we call interval notation. Basically a pair of parentheses with min and max values specified. All right. So this is my 95% confidence interval for little p, the population proportion of people worldwide that recognize Twitter. So let me write this down here again. I'll say that my 95% confidence interval estimate for p, the population proportion of people worldwide that recognize Twitter. Okay, I could specify my answer in interval notation. That's what the calculator outputs, interval notation. All right. I can do it in inequality notation. And I think I like the inequality notation best. In further sections, we're going to be estimating different things, not just p. So this inequality notation, I suppose, is preferred on test day and certainly in the author solutions manual. And again, you could display this graphically as well. Of course, this confidence interval estimate is centered around p hat by definition. Right. And again, the idea here is we've created a bucket which hopefully contains p. Right. Alright, so this is our 95% confidence interval estimate for little p. And again, the idea here is little p, the population proportion, right, I'll say will be contained in this range, hopefully, and we'll say with 95% probability or 95% confidence, hence the name confidence interval estimate. Okay? Alright. One more example I want to do before we call it a day. This one's out of the homework list. Number 18. On page 338. Let me turn there myself and we'll read us the problem. Number 18, gender selection. The Genetics and IVF Institute conducted a clinical trial of the Y-sort method designed to increase the probability of conceiving a boy. As of this writing, 291 babies were born to parents using the Y-sort method, and 239 of them were boys. Alright, we got parts A and B. I want to look at parts A and B. Alright, let's summarize the given information here. I'm going to make a little circle here showing that we've got 291 babies in this study, and 239 of them were boys. Right? It tells us that explicitly. Alright, so part A asks us to create a point estimate of the population proportion of boys born to parents using the Y-sort method. Right? So our goal, again, is to estimate the population proportion of boys using this method for all the parents for all time that use this method. Right? Alright, so again, our best point estimate of little p, again, remember, little p is unknown and really unknowable, we'll say is p hat. And that's, of course, equal to x over n, where x is the raw count of boys in our sample, and n is, of course, our sample size. All right, so that's really going to be 239 over 291, and that turns into a 0.821, and that is a point estimate for little p. Okay? Let's look at part B now. Alright, part B says, use the sample data to construct a 99% confidence interval estimate of the proportion of boys born to parents using the Y-sort method. Alright, so let me write that down. We've got we want a 99% confidence interval estimate for little p, where little p is the population proportion of boys for all parents of all time using this selection method. Alright, again, we're going to use one prop zint command. We've got stat, punch the stat button, scroll over and select the tests option, and then scroll down till we see one prop zint, and then highlight and select to call up that command, and we should see the following prompts. Get the calculator prompts us for a raw score for number of boys, a sample size, and a confidence level. Now if we scroll back up, we'll see, well, the number of boys in this sample was explicitly given to us, was it not? 239 boys. All right, so we don't need any sub-calculations here. We just plug in 239 for our number of boys. All right, our little n was 291. As you recall, our sample size was 291, again explicitly given to us, and the confidence level was 0.99, kind of a sharp or high level of confidence. All right, once you've entered in those values, scroll down and select Calculate, and we should get the following calculator output. Let me write it down here. Again, the calculator outputs this in interval notation, which is fine. So there's a range of high and low values, which hopefully captures little p. Notice the calculator also tells us p hat and n, just to remind us of where we've been, perhaps. Oh, we don't really need that. We're really looking for just the confidence interval here. This is my 99% confidence confidence interval estimate for little p, where little p is our population proportion of boys for all parents of all time using this method. Alright, in inequality notation, which again our author would probably use in our solutions manual and our examples in the text, this is another representation of our 99% confidence interval estimate for p. And again, we tend to favor this representation because you actually have to put the quantity you're estimating in the answer. And again, a graphic representation. P hat minus e in this example is 0.76346. P hat plus e, our upper bound for this interval, is 0.87915. This interval is of course centered around p hat, and of course we can make some kind of conclusion in a verbal statement that p, which is unknowable, little p, will be contained in this range. You can't be 100% sure, but we can be 99% sure, right? That was our level of confidence for this particular confidence interval. So with 99% probability or 99% confidence. Hence the name confidence interval estimate. Alright, that concludes section 7.2, and that's it. Thank you.